We are live. All right. Well, hey there, folks. Let's see. I think I have some announcements. Let's see. Or reminders, rather. So you've got homework due. What is it, like Monday, Wednesday, probably Friday, too, of week 2. So I've learned that with big classes, you can't give too many homework reminders. So I keep mentioning that. Oh, and another reminder, don't look up homework solutions. It's not allowed. You gotta come up with them yourself. You can get help from, like, TAs and Piazza and so forth, but you can't just look them up. And here you can see a schedule for today, things that I want to talk about. Anyone have any questions on anything before I get started? I see. Yeah, someone was asking about the homework. If you can't figure it out, send me an email. Cool. Okay. Well, then I guess I'll just keep doing what I was doing. Whatever. All right. So let me just pick up with what I was doing last time. This is what I ended on last time. So this is still from section 5.1. And so I drew this picture last time, and let me just remind you of what we said. We started off by picking some rectangle, capital R, in the XY plane. So R is the green part at the bottom of the picture. And you have some function which is defined on the rectangle and which is real valued and which is positive. Then this is what we did last time. We defined the double integral of f over the rectangle, and we defined it as the volume beneath the graph. Okay, so there's your definition of a double integral. It's the volume beneath the graph, and we might write it like this, or we might write it like that. And it's the 3D volume of this sort of cuboid looking object. So that's all from last time. So how about let's look at an example. Let's check out the function f of x and y equals 1 minus x, which doesn't even actually depend on y, but that's okay. It's defined on 0, 1 squared. This is just notation, by the way, for 0, 1 cross 0, 1. And we sometimes call it the unit square. So let me try to draw it in the picture that we have below here. So there's 1 on the x-axis and 1 on the y-axis. So my unit square is this square right there. Can someone tell me what's the graph of this function look like? Milan?
It would be a plane from, yeah, only dependent on the x variable.
Yeah, it only changes with x. It's like flat. If you move in the y direction, the function doesn't change. We can even figure out what its graph looks like by, say, plotting some points. Like, notice if, say, x is 0, then no matter what y is, we get that f is 1. So anytime x is 0, so like right here, for example, right here, all along this little line segment here, the function is equal to 1. And if x is equal to 1, no matter what y is, the function is 0. So it's 0 at every point down here where x is 1. Now, you can plug in some more points if you want. Oh, Milad, are you done with your question?
Yeah, that's all.
Okay, so you can lower your hand if you want. You can plot some more points if you want. I'm just going to assume you've already done that if necessary and connect the points that we already have. And now you can see what the shape looks like, or really what the volume of interest looks like. So it looks like a wedge. In fact, here's a 3D rendering of the shape. So the volume of this wedge is the integral of the function over that rectangle. How would we calculate that, though? I guess a wedge is not very hard, so you might already know how to find the volume of the wedge. Obviously, we're going to see harder shapes soon. Thankfully, we have some theorems that will allow us to calculate these integrals. So here's our first theorem for how to actually evaluate double integrals. And I'm going to come back to example 1 in a minute, but first, let me at least give you the formula so that we can actually calculate it. Okay, so theorem 1 gives us a formula for calculating an integral over a rectangle. And it says that the integral of a function over a rectangle is equal to this expression, which is referred to as an iterated integral, because you do one integration with respect to one variable, and then you integrate that with respect to the other. So let me clarify that a little bit. The integral inside the parentheses is with respect to y. If you perform an integration with respect to y, that means that you hold x fixed. You pretend x is a constant. Then, once you do that, whatever you get, it will probably depend on x. So, well, then you do the second integration of that function of x, whatever it is. So let's try applying this formula to the wedge, and well, let's see what we get. So according to the theorem 1 above, the double integral over 0, 1 squared of 1 minus x dA will equal Let's see. So I guess, oops, we do the x integration on the outside. And then on the inside, we do the y integration. Okay. When we do this first integral, we're integrating with respect to y. The thing doesn't even depend on y. So it's like we are integrating a constant right there, which just means multiply by y. That will give us 1 minus x times y, evaluated from y equals 0 to y equals 1. So any questions on that part? That's, I don't know, maybe the newest, trickiest thing that we're talking about?
Yeah, just a quick question. Can we switch the order of when we integrate with respect to x and y?
Yeah, indeed. Good point. So you might have noticed, like, what the heck is special about x? And the answer, nothing. So yes, you could integrate with respect to y first, and I'll give you that formula shortly. Let me finish up this one. So we're going to get the integral from 0 to 1 of 1 times 1 minus x minus 0 times 1 minus x. Second term is 0. So this is actually just the integral of 1 minus x, which is easy enough to integrate. That's x minus 1/2 x squared from x equals 0 to 1, which is, let's see, 1 minus 1/2 minus 0, which is just 1/2. Cool. Okay, so yeah, that answers that. So the volume of the blue wedge here, let me scroll up for a second. This thing right here apparently has volume equal to 1/2. And just like, oh crap, I didn't see the name of the person that was asking that question. Someone was just asking about whether we could interchange the order of integration, and indeed we can. So here's a theorem which gives us the formula if we had done the y integral first. So theorem 2 looks a lot like theorem 1, except now I should say the x integral first. Now we perform the x integration first, and then we perform the y integration. Because it makes sense that that this should be true, since x and y are treated symmetrically. At no point have we ever said there's anything special about x versus y. So based on that, let me ask the class a yes or no question. Nope. Different color. So now that we've seen these two theorems, here's my question. What is it true if I took the formula above and I interchanged the dx with the dy? So this formula right here, it's the same formula as above, except I flipped x and y. So yes or no, is this new formula true? Okay. So yeah, this one is a no. No, it's not. I saw some people commenting correctly. Oops. So the reason that it's not true is because I didn't interchange the bounds. So you can reverse the order of integration, as it's called, but if you do, you need to adjust your limits accordingly. Okay, you say no because I neglected to adjust the limits of integration. So this is a common mistake, something you'll want to keep an eye out for. It kind of makes sense though, because A to B, that goes with X, whilst C to D, that goes with Y. So you should always be having the X interval going from A to B and the Y interval going from C to D. Now, I could prove these two theorems, right? Theorem 1 and Theorem 2 are both equal, or those two formulas are equal. And I could do it using something that you probably learned in 20B, hopefully, maybe, and that is Cavalieri's principle. So let me ask the class, can I see like a show of, excuse me, yeses or nos for people that remember having learned Cavalieri's principle? So say yes if this is familiar, say no if it's not familiar. Okay. For those who are saying no, I'm wondering if you took 20B at UCSD, because it's like technically in the curriculum. So I'm wondering if maybe like your professor skipped it, or maybe you forgot. It's possible you forgot because it doesn't come up that much, but let me say what it is. It's a principle for calculating volumes, and it's pretty general. It has wide application. It allows you to calculate a bunch of volumes as sort of an alternate method. So there's a lot of problems where you have some formula to find the volume. Alternately, you could use Cavalieri's principle. So this is like a second method that you could use to find all sorts of volumes. And here's what it says. Suppose you have some three-dimensional solid, which I am calling S. And you want to calculate the volume of S, right? How much 3D space does it take up? If you can find the area of a cross section, specifically, you need the area of a perpendicular to the x-axis cross section. That is to say, if I say label the x direction as pointing that way, then if you pick some point, let's call it x, and imagine taking a knife and slicing this shape, okay? You slice it vertically right here. And when you slice it open, you see a cross section. There's your cross section in red there. And suppose that it has area A of x. And that cross section is perpendicular to the direction of the x-axis. In this case, in this setup, you can find the volume by integrating that cross section from where the shape starts up to where it ends. That is to say, from x min up to x max, those being the minimum and maximum x values that the shape subtends. Okay, so yeah, that's Cavalieri's principle. Like I said, it's pretty general. There's going to be a number of problems that we're going to see in later sections where you could alternately solve them using Cavalieri's principle instead of using whatever formula we're giving you at the time. So why don't we try using it? I'm going to do an example now and use Cavalieri's principle to find the volume of a sphere of radius r. Like I said, you could also use it to prove the two theorems that I already did, but you can read that in the book if you want. The sphere is a cool problem because the sphere is like the most perfect three-dimensional shape. Among all shapes, it has the highest degree of symmetry. It has an infinite number of axes of symmetry. It maximizes the volume for a given fixed surface area. It's a beautiful, highly symmetric shape. So if there's any shape we would like to find the volume of, it would be a sphere, or perhaps I should say ball. The thing is, mathematicians didn't know how to derive this formula until Newton invented calculus. So it's kind of amazing how easy this is going to be, given the fact that it stumped mathematicians for like 2,000 years. The way I'm going to do it is I'm going to set up a coordinate system. So how about I just choose the x-axis to point to the right. And I guess we can have the y-axis point up. Apparently, the sphere extends from a minimum value of -r up to a maximum value of +r, since the radius is r. Now, we need to take our knife and cut this thing open, okay? Maybe some of you noticed that at the beginning of lecture, I had a picture of an orange. So you can imagine slicing open an orange. What's the shape that you see when you slice open an orange? You see a disc. So let me try and draw one of those. Suppose that I slice it, say, right there, okay? My cross section is going to look like a big disc. So there's my cross section. Let me ask you all a yes or no question. If how about, sorry, let me say it like this. The radius of the disc in the cross section is r. Yes or no? Oh, nice. All right, good, very good. Yeah, you guys are getting this correct. Okay, so let me give it another name. How about I'll call it, let's call it little r. Now I can figure out what little r is because I know that the radius of the sphere is big R, and moreover, this distance right here is x. So I have a right triangle right here. this thing right here, that's a right triangle. So I can just do the Pythagorean theorem to figure out what little r is. And when I do that, I will find that little r is the square root of big R squared minus x squared. So that's via the Pythagorean theorem. Well, now, and by the way, that was just the hardest part of the problem, just there, just now. So let me know if someone wants an explanation on something. I can then find the cross-sectional area, since it's a disk. So the area is pi r squared, which is pi times the square of big R squared minus x squared. The square and the square root cancel each other out, actually, and we get pi times big R squared minus x squared. So the volume of the sphere would be the integral. Let's see, the minimum x value is negative r, the maximum one is r, so it'll go from negative r to r. The cross-sectional area was just calculated to be capital R squared minus x squared. Now, I could solve this. This is, like a straightforward 20b integral right now, but I'm going to do an important shortcut right now. I'm going to exploit symmetry. So this is one of my favorite things to do in this class, and it's kind of tricky. Remember from 20b that if you have an even integrand and the bounds are symmetric, then you can just do half the integral and double it. Okay, so I'm going to guess that about 2/3 of you, maybe half of you, know what I'm talking about, and about half of you don't. If you don't, stick around for office hours, and I'll talk about it for another 5 minutes. So here, this right here is an even integrand. And like I said, I can explain more after I finish if you're not sure why. These are symmetric limits. Sorry, hold on a second. Hence, I can write this as twice the integral from 0 to r of pi times r squared minus x squared. Cool. Okay, so that's one of my favorite little simplifications to do by exploiting symmetry. We are going to come back to that multiple times in this class. And now I'm ready to actually compute the integral. So that'll be 2 pi r squared x minus 1/3 x cubed, evaluated from 0 to r, which is 2 pi times r cubed minus 1/3 r cubed, which is 2 pi times 2/3 r cubed, or 4/3 pi r cubed, the familiar sphere volume formula. So there, just like that, we did what took, mathematicians 2,000 years to come up with, and it was that easy. And we used Cavaliere's principle. Any questions on this? Man. Okay, this is a quiet class. Okay. Well, making good time.
Oh,
I guess.
actually, I'm sorry.
Mhm.
Can we still use the split even the limits are not symmetric?
Not exactly, no. You would have to make them symmetric. You could split up the integral into a part that is symmetric, and there might be some left over that isn't. But yeah, you can't do that trick unless the limits.
So I mean, for example, if the limits is going from 0 to 2r, then can we just still use like 2 times the limits of r goes to 2r, or like 0 goes to r, something like that?
In special cases, in that case, you would need a function that is like symmetric around a different point instead of symmetric around 0. So like, for example, what if you wanted to integrate, how about x minus 1 squared from 0 to 2? This function right here is symmetric around x equals 1. Symmetric, that is to say even, about the line x equals 1. You can see that from the graph. The graph looks like this. There's 1. So thus, this will be twice the integral, say, from 0 to 1, or from 1 to 2, either way. How about, I'll just say from 0 to 1, x minus 1 squared. So that would be sort of an exception or a similar case. Does that help address your question?
Yes, that was my question. Thank you.
Mm-hmm. Cool. Yeah, good question. Okay. If there's nothing else, then I'll go on to 5.2. Oh, Ollie?
Yeah, I have one question. So when we're using this principle, a of x, like the formula we use, is really dependent on the shape, right, of the intersection. So
yeah, the cross section.
Okay. Thank you so much.
Mm-hmm. Yeah, and that's actually like the hardest part, is figuring out what that is, because it usually involves geometry. So in fact, I'm glad you mentioned that, because that reminds me. So this whole sphere problem, I did it because of one of your homework problems. You've got one hard homework problem that is related to all this. It has to do with like some sort of vaguely wedge shape. It looks kind of like a wedge of cheese or of brie or something. Yeah, cut from a log. That's kind of a tough problem. And you'll do it kind of similar to how I did this one. You may have to do draw a similar sort of triangle. So yeah, this is meant to sort of help everyone with that homework problem. Okay. So moving on to section 5.2. Now, I want this class to take a trip down memory lane for a second. Imagine you're back in 20B and you're learning about integrals. The first thing that you learned about integrals in 20B was that they are the area under the curve. Next, you learned that they're also equal to the limit of Riemann sums. Well, guess what? The same thing is true in this class, except now we're talking about functions of 2 variables. But it works analogously. So previously, we said a double integral in this class was equal to the volume below the graph. Now, I'm going to tell you that I'm going to give you an equivalent definition in terms of Riemann sums. So the problem is they're kind of ugly. Now, you don't have to take like great notes on this. I would rather actually that you just sort of watched and paid attention. It's probably going to be a little bit confusing, but just bear with me over the next few minutes. So here's the setup. Suppose again that we have some rectangle in the plane, and we'll call it R. And suppose again that we have some function which is defined on R and is real valued. Notice I am not requiring that the function be positive. Now, so here, this green rectangle, that's R. What I'm now going to do is split it into a whole bunch of equal subrectangles. So I'm going to do that by splitting the interval from A to B into n subintervals, and similarly, I split this one into n subintervals, so we get a whole bunch of little subrectangles. In each one of those subrectangles, I'm going to pick some sample point. Now, maybe it's in the upper left corner, maybe it's in the lower right corner. It actually doesn't matter. So like in the first subrectangle, maybe I pick the upper left corner, and I'm going to call that C11. I'll pick some other point in the next subrectangle. Maybe I'll pick the center. Call that what, C13 for the next rectangle, and so forth. These are called sample points. I can now form a Riemann sum by defining what I will call S sub n, and it will equal the sum over all indices I and j of f evaluated at the sample point times delta x delta y. Delta x delta y, by the way, is exactly the area of the subrectangle. The area of R sub ij. They all have the same area. Their width is always delta x, and their height is always delta y. So this right here is it's like a two-dimensional Riemann sum. And let me scroll down for a second just to jump ahead to show you a picture of what it looks like. It's hard for me to draw, but basically it represents a bunch of these like cubic rectangular boxes. Let's call them boxes. So like there's one here, and one of the terms would be the volume of that box, and then there's another box, and one of the terms would be the volume of that one, and the sum is the sum of the volumes of all those boxes. So with that said, I can now define what it means for a function to be integrable. F is said to be integrable on the rectangle R if the limit as n goes to infinity of that Riemann sum S sub n exists. So the limit has to exist, and moreover, it doesn't matter what choices of sample points we made. So no matter what sample points we used, we always get the same value for that limit. In that case, we say that the function is integrable, and we denote the value of that limit by the double integral of f over r. So there's a few different ways we write that. We might write it like this, which is the same notation we've already seen. We might write a dx dy. We might suppress the argument of f, okay? So sometimes when it's convenient, we sometimes write f instead of f of x and y. when the context is clear, okay? So that's why you might also see the integral written like this or like this. Whew, okay. There's your definition of integrable. Now, remember in 20B how like you learned Riemann sums and they were kind of tedious and tricky, and then you learned an easier way to do integrals and you stopped using them. Same thing here. So we're actually not really going to use Riemann sums much in this class. So if you were confused by any of what I just said, not a big deal, actually, because we're not really going to use it. I just needed to mention it to sort of put ourselves on a firm footing. Now, you're welcome to look up details in the book. It has more details than the ones that I just gave you. Moreover, these are very important, just not so much for this class, but Riemann sums are super important for numerical analysis, CS, engineering, pretty much anything numerical, they're really useful for. So just, throwing that out there, you may very well end up working with these guys one day. Also, like in 20B, this definition coincides with our earlier integral definition. So definition of integrability that I just gave you, this gives the same number as the earlier definition that we gave in terms of volume. In other words, I'm saying that the volume of these approximating boxes approximates the true volume underneath the graph of f when you let n go to infinity, if the function is positive and continuous anyway. If it's not positive, then you have to adjust that statement slightly, and you would call it like the signed volume. If it's not continuous, well, I'll talk a bit more about that later. So in fact, actually, I'll talk about that right now. So here's a theorem. If the function is continuous, then it's integrable. So I went to MATLAB when I was writing this lecture because I wanted to show you all some pictures of what, well, I was going to say continuous, but most functions you see are continuous. So I wanted to show you some pictures of functions that are not continuous. So here's some that I went and plotted on MATLAB. Like the first one, that would be a piecewise function that's not continuous. Okay, like it's got one piece up there and there's another piece down there. Those are two separate pieces and they are discontinuous right here at the boundary of their pieces. That would be one example of one type of discontinuity of a function of two variables. On the right, however, we've got another example of a discontinuity. This is for the function 1 over the square root of x squared plus y squared, which is an important example, by the way. We're going to see this example in this class multiple times. And it has a discontinuity at 0. So this MATLAB wouldn't show me the whole thing because the graph blows up to infinity right at the origin. So there's another discontinuity. In the case on the right, the function is discontinuous at a single point. In the case on the left, it's discontinuous at a whole set of points, right? Like all along this boundary, the function is discontinuous. So any questions on this? Good. Okay. Then, wow, really good time. So I guess I can give you Fubini's theorem. Here's Fubini's theorem. I know it's like a lot of theorems. Fubini's theorem is actually just a rewrite of the two earlier theorems that we saw today. In fact, can someone tell me what's the difference between Fubini's theorem right here and what I called theorem 1 and theorem 2 from earlier today? I want us to really be paying attention. What the heck is the difference between this and what we already saw today? Ollie?
Isn't it just saying that they're equal to each other, so it kind of like combined both of them? Like, does it matter what variable you do?
It does combine them, although I could have combined them earlier as well, actually. That was kind of implied. There's one other little difference. Let me see if anyone's gotten it in the chat. Oh, okay, yeah. So I didn't mention, did I mention continuity? Okay, I didn't actually even mention, did I mention continuity earlier? Well, one thing I did mention earlier was that f had to be positive. In this case, I make no such requirement. So this is just the slightly more general version of the earlier theorem. Maybe I shouldn't say it's slightly more general. It's slightly different, but it's essentially the same. For most of your purposes, as far as you all are concerned, it's basically like a repeat of what you've already learned. And it just says that if you want to evaluate an integral of some function over a rectangle, then you can evaluate it by doing two iterated integrals. And you can either do it first with respect to y and then x, or you could do it first with respect to x and then y. And you should get the same thing either way. By the way, this is a super useful and important theorem. I actually used Fubini's theorem in my dissertation in kind of a big way. So yeah, it's a super important theorem. Let's see. I guess that's all I have. I can actually end a little bit early. Maybe I should end early while I have the chance, and because I'll probably end late at some other point. So yeah, I'm gonna stop right here, and you know, we'll pick up on I guess 5.3 next class. So yeah, that's it, folks. Hang around to answer questions. Oh yeah, if anyone wanted. If anyone forgot what even and odd was, I'm going to talk about that. To everyone else, I'll see you on Friday. So let me just remind now, I'm going to guess that about a third to a half of the class forgot what even and odd was. So let me just say what that is. A function f is even if f of negative x is the same as f of positive x, you know, for all x in the domain. So in other words, when you plug in a negative x, the negative just disappears. So like, for example, I used the even oddness of the function r squared minus x squared in the sphere calculation today, because look what happens if I plug in negative x. Get r squared minus negative x quantity squared, and the negative sign gets squared and goes away, right? That negative sign, it gets obliterated right there by the square. So we just get the same as f of positive x. Let me give you the definition of odd, because the two go hand in hand. A function, let's call it g, is odd if g of negative x is negative g of x. So let me ask you all a yes or no question. How about if h of x is x times the square root of 1 plus x squared, then h is odd, yes or no? Wow, this class is pretty good, actually. Wow. Maybe you all are better than my previous 20E classes. Good, okay, yeah, nice. Then finally, I'll just remind you of the symmetry that I was using from 20B. So from 20B, we have two properties. So for one, if f is even, then the integral from negative a to a, where a is just some number, of f of x dx is twice the integral from 0 to a of f of x dx. And there's a similar one for odd. So if g is odd, then the integral from negative a to a of g of x dx is what? Someone tell me what this one is. Zero, good, okay, yeah, very good. So yeah, those are called symmetry properties, or symmetric integrals of even and odd functions. So yeah, I just wanted to mention that, just thought folks might have forgotten it. And yeah, I guess that's it. So if anyone has any questions, go ahead and fire away.
Oh, actually, yeah. Can you explain the difference between the Cavaliar's theorem and Frobenius theorem? I feel like from the looking at it, they're just the same, but you said something about f is bigger than 0. I didn't quite get that.
You said the difference between what?
The two theorems, the Frobenius theorem and also the did I say that right? The Cavaliar's theorem?
Cavalieri's was different. Cavalieri's did not involve iterated integrals, but the two that I gave before it, I guess. So when I get, okay, so actually, maybe I should have been more clear on this. At the time when I gave this definition, we had only defined the integral for positive functions.
Okay.
Right? Like what's the definition of a double integral? We said it's the volume beneath the surface.
Perfect, right.
When the function is positive. I never said what it was. when the function was negative. So it was only after I introduced the Riemann sum definition that now we're allowing functions to be negative. And if I still wanted to talk about volume, I would have to call it the signed volume instead of volume. This is analogous to what you did in 20b, where if you had a function that's both like positive and negative, and you integrate it from A to B, then what you get is the signed area, where like this area is normal positive area.
Right.
But the one down beneath the x-axis would actually be subtracted instead of added. Add this one and subtract this one. The integral from A to B of f dx is the signed area between the graph and the x-axis. So I could say the same thing about volume now, signed volume.
Okay, so basically the Cavalieris principle, the theorem, it didn't introduce when the surface is below 0.
Yeah.
Okay.
Oh wait, sorry, did you say, sorry, it's kind of hard to understand you. Did you say Cavalieri?
Yeah.
Oh yeah, that one, Cavalieri's was actually, doesn't even necessarily have to do with double integrals. It's a volume concept which we actually learn in Math 20b. So Cavalieri's is kind of separate from these other theorems.
Okay.
But you can actually derive them from it.
So I mean, when I was looking at the figure from the textbook, the 5.1.8, one that you use for the Cavalieri's theorem, and eventually when you derive from both the perspective of x or y, they came up exactly the same equation as the Fubini's theorem. So I was assuming those like two theorems just actually kind of the same.
Okay, let me look for what you're talking about. You were looking at, did you say a figure?
Yeah, figure 5.1.8 is at page 267.
Yes, okay, right. So I actually mentioned this today. I said you can use Cavalieri's principle to show that this formula and the earlier one, this one, give the same thing. Oh, wait, is that right? Hold on, actually, let me look at the book. Yeah. Right. Because both of them are equal to the volume of that.
Underneath the surface, yeah, except there one is derived between on a perspective of x, the other one is from a perspective of y.
Yeah. So here, in fact, I can even show you.
Yeah, I remember seeing that on the note as well. The figures on the note that you said you couldn't really draw. And
yeah, right. It's based. Actually, I showed this actually when I first taught the class, but yeah, like you either make cross sections perpendicular to x, and I guess the one I draw is y. So if you make cross sections perpendicular to the x-axis, let's say this is the point. Let's just call it x. Can you tell me what's the area of this cross section?
oh, just be delta x times fxy. From
The area.
Oh no, actually, actually it's from it's delta y times fxy and from c to d.
Yeah, so it's right. So it goes from C to D. Yeah. And And yeah, if you wanted a thickness, you would throw in the delta x there.
Right, and that becomes the double integral to calculate the volume.
Yeah, right. So yeah, this thing would have area equaling the integral from C to D f of x, y, dy. And then, so yeah, you would just integrate that from A to B, and that's how you would get one of the two formulas. And similarly, you could have found the other cross section.
And the y-axis, right.
Yeah.
That's what I was saying, that the Cavalieri's principle isn't that like just almost the same as the Fubini theorem in this case? And, you know, it's...
Let's see. Well, Cavalieri's, for one, it was just for positive functions. So we haven't talked about the notion of negative volume or signed volume. Fubini's does not specify that the function has to be
I see.
positive.
So that's basically the only difference between them, right?
Yeah. So I mean, let me look exactly at Cavalieri. So they're a bit imprecise. Now, it depends on how deep you want to go into the analysis with this. Like, we've actually told you some lies. You can have shapes that are sort of fractal-like and have very rough edges, for which you can't really define the volume, at least not using these definitions. So if you had, I don't know, something like a sea sponge, for example, it's very porous, it's very fine-grained, it's very rough if you zoom in. In that, for a shape like that, the Cavalieri's principle definition would break down because you wouldn't have a good notion of what volume, area, or cross-sectional area would be. Fubini is more rigorous. It's built on the definition of a Riemann sum, which is good, although it's not great. There's even that definition breaks down again when you consider rougher and more complicated shapes. Although to handle the cases that it breaks down in is beyond the scope of this class. You would have to learn about that in a real analysis course. Although
Thank you.
Yeah, sure. It's really interesting though. This is basically measure theory, what we were talking about.
Because when I didn't read through 5.2 yet, and then when you introduced the Fubini's theorem, when I saw that, I was like, isn't that exactly just the same as the Cavalieri theorem? And I got a little bit confused over there. So yeah.
No, yeah, it's a good question.
Thank you so much. That answered my question.
Yeah, thanks for asking.
Oh, and for the homework problem, the PP1, do you want us to just kind of discuss it or want us to like prove it as well?
I think you should prove it. Yeah, like show detail.
Okay, so we can just kind of use the even or odd the ones that you just said from 20B to
Yeah.
Right? We can. Okay, great.
You have to be a little bit careful because now that we have functions of two variables, it can be even in one of the variables or odd in one of the variables, and it's.
I see.
So you have to think about it a bit more carefully.
Got it. Thank you so much.
Yeah.
Okay, you have a good day. Bye.
All right. Yeah, you too.
I actually had a quick question about that as well.
Mhm.
Is that just the PP1? That's not something that's in the book. That's just the question that's specifically written under the homework tab, right?
Yeah.
Okay,